not a whole lot. I want to give you a reason to use Maple. Okay, basic stuff. So you don't have to be a programmer. You don't have to have taken a class in this to do some very useful things. So a lot of these functions, when you're, especially when you're finding a particular solution, and they give you, two initial conditions if it's a second order differential equation, right? You have to differentiate your function, plug in a value, solve for the constants, and then the derivative, plug in a value, right? So you may be differentiating nasty functions and all that. I just want to show you some of the capabilities of what this can do. Not the Maple Cloud. Over here they have some predefined things, some templates. So over in expressions, for instance, you can define a function pretty easily. F, you can call it whatever you want, it doesn't matter. Let me zoom in on this, there we go. All right, so we usually call them y. So y, and what it does is it defines this function and it takes an input x and it assigns it an output value. So whatever it happens to be, maybe 2x plus, plus e to the negative x. So I type that in as exp to the negative x. Okay. All right, and just hit enter. Okay, and it has it there. So this is it can work as a computer algebra system as well. You don't have to just do programming and graphs and all that. If I right click on this, it'll let me, for instance, evaluate procedure. Say I want to evaluate it at 0. Parameter value x, it calls it a parameter, whatever, but 0, oh, the value of the function is 1. Okay. I can also right click and differentiate with respect to x. There's its derivative. I can hit the evaluate procedure, evaluate that wherever I want. Oh, it's also 1. Okay, great. So differentiate, and it tells you what it does at each step, so you have this kind of list of all the commands that you've done. But even better than that, simpler than that. I got that function defined, and all I did was find y of 0. 1. Y prime of 0. I was playing around with this the other day. It recognizes that as the derivative operator. Y prime of 0, 1. Y double prime of 0, 1. Yeah, there it goes away after that, the x term. So you can evaluate and you can quickly find the derivatives. I think even if you have a parameter in here at like c, say it was e to the whatever, well, or c e to the x, e to the negative x. I think it will recognize that as a parameter because I'm differentiating with respect to the variable x, and it keeps it in there, that c. Okay. So it can quickly find derivatives, antiderivatives, evaluate, and it uses function notation as well because it has that defined as y, that function.
What's the arrow operator?
The what?
The x is an arrow,
Oh,
or is that equal?
it's taking a real number x input, so it's a function of one variable, spits out an output, so this is just like a function operator. It takes an input, that's its output, according to what x is.
Gotcha.
Yeah. This is the assignment operator. We're assigning that function to the variable or constant named y, and then I can evaluate it.
So it's like saying y of x is that.
Mm-hmm.
Okay.
Mm-hmm. Yeah, I just define that function y. Yeah, you can find its first, second derivative very quickly. You don't need to do with plots command to do that. That's just using the computer algebra system. Now, if I wanted to graph that, let's see what we could do. Plot y of x between x equals, say, -1 to 2 or 3. It might not like that c value. I don't know how I can define it. C equals 1 if I just put it in there. Does it do it? No, it doesn't like that. Okay. All right. So I can work on that. But say c is 2, just for the sake of our purposes. Reevaluate that. We got y of x. Let's take out that command c equals 1. can plot it very quickly as well. Simple command, plot. It's not three-dimensional, so you don't need plot 3D or implicit plot or anything like that, but you leave in function notation. Plot y of x for x in that range. Okay. All right, and it's it's on all the computers here. So if you're near a computer lab, boom, you run in there and work on it in there. All right. All right. Let's start with homework questions. Let's do that first.
Apparently everyone did it perfectly.
Yeah, I like that. All right, let me start this from the end is in sight. We're on the second half of the term, so it's literally in sight. We're on the same page. We're on the last 5 weeks.
Are we having a test like next week sometime?
We'll have a quiz this Thursday. It's been a while, but the exam, I don't think it's next week. Is it week 8?
Yeah. Okay, the calendar.
Okay. Yeah, right now we're in week 6, so that's a couple weeks out. A couple of weeks. I think it's Thursday of week 8, I believe. All right, so we're feeling like we're masters of the linear higher order homogeneous differential equations. Okay. All right, let's go to work.
Yay.
Okay, so today we're talking about, we're going to talk about simple mechanical vibration. So a basic model of a mechanical, just a mechanical system is a mass on a spring. To make it a little more complex, say there's a dashpot. I've never heard of that before, dashpot, but it looks more like some sort of a damper, okay, or shock absorber. So inside that maybe some sort of fluid or just hydraulic, just air in there. But that could put a damping force on the oscillation. Okay. So just to define some things. So x here represents the distance from equilibrium position. So at rest, with the spring totally unstretched or compressed, this would be the equilibrium position. Okay. And this thing is just some mass on the spring. Okay. And so let's be precise and let's define our things here. So let x of t represent the distance of that mass from its equilibrium position. Okay. So there's a way to distinguish whether the string is stretched or compressed, because if it's 1 centimeter or 1 inch to the right versus 1 inch to the left of equilibrium position, we want to distinguish that and not just say x is equal to 1, right? So we assign a sign. We put a sign on this. So negative is when it's compressed. And x is positive if the spring is stretched out of its equilibrium position. And when we take x less than 0 to be for when the spring is compressed. Okay. So Hooke's law talks about this. The force, basically due to a spring, the force exerted by the spring is proportional to the distance that is stretched or compressed from its equilibrium. So the more you stretch it, the more force there is pulling it back to its equilibrium, right? And it's proportional to the distance from equilibrium position that it is. So Hooke's law, and he has a Hooke's constant and all that stuff, all sorts of stuff to do with springs. So Hooke's law says that the force exerted by the spring force, is proportional to the distance that spring is from, or the mass is from its equilibrium. However, we got to get the sign right. If the spring is stretched out to the right, which way is the force exerting on it?
Left.
Right, to the left, right? So it's opposite. Now, if the spring is compressed, which way is the force exerting on that?
To the right.
To the right. So always opposite the distance x. It's always opposite the direction that x is in. So just like the way, you're going to see some similarities in models that we've seen before, but there's a negative there. Okay, so it's opposite the direction that the spring is. And this is the restorative force. That, it will tend to bring the spring back to equilibrium. Okay. You might notice that just what we talked about, that spring force or restorative force is less than 0 when x is positive, and that force is greater than 0, it acts on the right when x is negative. So it acts in the direction opposite the position of the spring or the mass. Okay. All right. So it's gonna, when you let that thing go, it's gonna obviously oscillate back and forth, and depending on the strength of the damper in that dash pot, that's going to dampen the oscillation, right? So we're going to be considering that. But it'll go back and forth and eventually stop oscillating altogether, right? Stay at equilibrium. So what we're after is, well, first a model for the position at time t. Okay, we're going to come up with a model involving a differential equation, and then look at different cases. Okay, based on the strength of the damping force. Okay, so this is like, think of it like some sort of thing in there that's what's that called? Like a gasket pushing back and forth, and that's going to slow it down. There's going to be some force exerting in there. So let's talk about that force. So the damping force and the book refers to that as R, which could be kind of confusing because I would think of that as the restorative force of the spring R, but S stands for the spring. Okay. All right, so F sub R, that force exerted on it by the little dash pot thingy is actually proportional to the velocity of the vibrating mass, right? Just like when you drop an object, we talked about this, that the force of the air acting on it upward is roughly proportional to the velocity of the object. So the faster it's falling, the larger the air resistance pushing back up on it, right? So this acts in the same way. This thing is just moving side to side. It's not in free fall, but it is proportional to the velocity at which that spring is vibrating at any instant. And it acts in the opposite direction as well. okay? So C is greater than 0, as will this constant K. Since I'm forcing it to be negative out here, we can take K, assume K is going to be greater than 0 to make sure that we get the sign of that force correct. Okay. Now, velocity of the object, we're talking about motion, it's just back and forth, so velocity is the derivative of x, right? The position. So that's dx dt.
Why wouldn't the dampener force be in the same, it seems like it would be opposite the direction of the spring, because if the spring is pulling it back, it should be acting against the spring force.
Yeah, that's why you got the negative out front.
Oh, so that's negative, that means opposite.
So if the velocity is positive, that means if it's moving to the right, that force is
Okay,
negative.
gotcha.
Yeah.
Not
If the
position,
velocity is
not
negative, this
position, again.
this takes a little imagination. If the velocity is negative,
Gotcha.
then we got negative of a negative value if c is positive, and we get a positive force here. So when the spring is moving to the left, the force of the restorative force of the spring is pushing it to the right, as well as the little piston or whatever it is in the dash pot. Okay.
So one's a velocity and one's a position. K, negative K is the position, and then negative.
K is not position. K is a constant, but x is position.
Well, I mean, K is multiplying towards
Mhm.
the position,
Mhm.
and C is multiplying towards the velocity.
Yeah. So they're just forces from different things. Yeah. And this one is just like wind resistance. It's proportional to the velocity.
Yep.
Yeah. All right. So this force right here is the one from the dash pot, not the spring itself. And it's, again, in direction opposite the motion of the mass. Okay. All right, so from Newton's second law, we've seen this before. Newton's second law says that force, total force, mass times acceleration. Okay, so again, if we write acceleration, well, acceleration represents the second derivative of the position, so this would be m d squared x dt squared, get my notation right? So second derivative of the position. And if we equate these forces, we have the following equation. So on one side, the force is equal to m times, well, I'm just going to call that x double prime at this point, okay, is equal to the sum of the other forces. So the restorative force from the spring plus the force exerted on it from the damper in the dash pot, okay. All right, and adding these together, f sub s was negative kx plus f sub r was negative c dx dt, so it's just minus c, and I'm going to call that x prime. Yeah? Okay. Now, if I put those all on the same side of the equation, I like these minuses on the other side, I would get m times x double prime plus cx prime plus kx equals 0. Okay. So, hey, lucky for us, this is exactly the type of differential equation we've been dealing with, right? Except we're calling it x instead of y, but it's linear in x. M, c, and k represent constants, so it's second order, linear, constant coefficients. So this is second order, linear, and constant coefficients. And this is if those are the only forces acting on it, okay? The damper inside the dash pot, that little, or it's almost like a plunger going back and forth, it's gonna exert pressure on it, and the spring constant. The book talks about if there's another external force, wait, was it CS prime? Yeah. Plus kx equals some sort of f of x. Now this is if there is some other external force acting on it, okay? We are going to disregard that, and we're just going to talk about the spring system itself, okay? So you end up with a homogeneous equation, okay? All right, well, we know how to solve that generally, right? A couple cases to consider. Let's start a new page, keep it clean. So first, undamped motion, completely. Now, undamped motion is when there is no damping force. In other words, if there is no dash pot, if it's just a mass on a spring with no dash pot slowing it down. So undamped would be if C equals 0, that constant. So it takes away the force from the dash pot. So it takes away this damping force, F sub R. And that's all we have. Okay, so with C equal to 0, what's the equation we get?
Kx.
R squared, mx double prime plus k,
Yeah, we'd have mx double prime, C is 0, so plus kx equals 0. And if we divide through by m, x double prime plus k over mx equals 0. Okay, where k over m is going to be, again, a positive constant. So here's the deal. This is a positive constant. And if we were to put in the solution, our method right now of solving this equation would be to, okay, well, we let x, in this case, not y, but suppose x has the form e to the rx. Then we would get a characteristic equation from this, right? What would that characteristic equation be?
R squared plus k over m. You want to use like y or something?
No.
Because
Oh, x equals e to the rt. Of
yeah,
course.
something not.
T, independent variable, t. So x equals e to the rt, we get what?
T squared e to the rt.
We would get r squared e to the rt, and I'm going to take out the e to the rt because that's what happens, plus k over m equals 0. What kind of equations do we get? Or what kind of solutions? Yeah. Mm-hmm.
Wait.
K over m is positive. We're gonna get complex solutions. So we get r equals, subtract that, I'm gonna have negative k over m, take the square root. So we're gonna have plus or minus I pops out of it, and then I'm gonna have left in there k over m. Okay, so two imaginary solutions. And they're purely imaginary, 0 plus or minus I times root k over m. But they're distinct. All right, so what does the equation look like when we get this case? You remember what happens when we got imaginary or complex with real part 0?
The real part is
What's that? They're different, yeah, they're different, because one of them's gonna be negative I times root k over m, and the other one's positive I root k over m. So they are distinct. We're not gonna do, you'll never be asked to deal with repeated imaginary or repeated complex roots of the characters.
One attributes to cosine, one attributes to cosine.
Yeah. So we will get cosine and sine. Oh yeah, but so you can go right to cosine and sine. You can get the sine terms together, the cosine terms together, and have faith that the coefficients at the end turn out to be real numbers. Okay. So in this case, we would get C1 cosine, and this is the imaginary part. 0 is the real part, and the imaginary part is what goes in the argument of the cosine and sine function. Okay. What I'm going to do is call that, well, yeah, sure, let's write it out for a second. K over m t plus C2 sine root k over m t. Okay. All right. One thing further, the book does call this omega naught. Okay, omega naught is square root k over m.
Shouldn't one of them be negative in there? The plus or minus?
The C should take care of it.
Or the,
The C will take care of it because the general solution, C could be a positive or negative constant. Yeah. So we did a little bit of the derivation where these come from. Yeah, there's generally an I out there. When we solved it, there was some, we called it D for a second. We could have complex coefficients, but when we combine them, the imaginary parts drop out. And just, yeah, we're going to go right to the real solution. Okay, so it'll be cosine and sine. When it's a complex number with a non-zero real part, then you get the e to some power in front of all of it. Okay? So this is a general, this is a specific case of that because our real part was 0. You could imagine it outside an e to the 0t. So it does follow that case as well. All right. So this is our function for x of t. Okay. So some things we could say about it. It's not a simple sine or cosine function, but it's still periodic, right? They share these parts of them. C1 and C2 are independent. They could be any constants, right? But the periods are the same on both. So the period of this function is the same. Okay, it has one single period. Okay, in fact, and it's omega naught. So the book does some fancy footwork on this. So it's not a good sign when you have to bring a trig book to your differential equations class. The book does some fancy stuff, and they say, oh yeah, you can recognize that you can write that as a single cosine function. Yeah, and there's a way to do it, but we're not going to worry so much about that. If we can write down the solution, the function, then we're good. Okay. But some things we can note about it. First of all, its period. Anybody remember how to find period? What would be the period of this function? That talks about the frequency.
2 pi over omega naught.
2 pi over that. Yeah. You guys might remember it like this. A cosine bx plus whatever it is, h they always call it in the book. So that contributes to the period. The period is 2 pi over that. Okay? So we're calling it omega naught. But the period is 2 pi over omega naught. And that just talks about how long it takes to complete one full cycle, back and forth of that spring, back and forth to the starting positions. Okay, that's the period. Time. So period talks about the time for one full cycle. One other thing that this model predicts is that will the spring ever stop oscillating, the mass on that spring? No. It's just gonna keep going back and forth, there's nothing to dampen it. Okay, the frequency, on the other hand, is just the reciprocal of the period. So 1 over the period, right? So that's omega naught